Hello friends, welcome to this video. So in this video we'll be discussing a very interesting concept of modern physics that's called AdS CFT correspondence. Now AdS CFT correspondence is basically, it's a very, some people assume it to be a very difficult concept because it's related to string theory and everything. But the concept is very simple, so we will be understanding the concept in layman terms, okay, not equations or something, okay. So AdS refers to anti-de Sitter spaces. Now what are anti-de Sitter space? That's one type of space and it's like with negative curvature, and for that you need to learn advanced mathematics and geometry, so we'll not be discussing the anti-de Sitter spaces in deep, but that's the full form of AdS. And CFT is conformal field theory. So basically AdS CFT correspondence is a type of correspondence which links two very different kinds of theories in physics. So AdS CFT correspondence, suppose imagine a sphere. Now CFT is the boundary of the sphere, it's related to the boundary of the sphere, and the AdS is the space that sits inside the sphere, inside the sphere. Now obviously AdS, the anti-de Sitter space, that has a higher dimension than the boundary, obviously, because boundary is two-dimensional after all, just the surface area, and inside the sphere you need to consider the volume, so that's of a higher dimension. Now AdS CFT correspondence states that between the CFT, I mean the boundary, and the anti-de Sitter space, the inside of the sphere, there is a sort of dictionary, a sort of dictionary that, so everything in the boundary has an exact counterpart in the interior, and there is a sort of dictionary or a sort of some rules according to which this happens, okay. So how this is important in physics, for instance, information paradox, the black hole information paradox. Now some modern researchers are suggesting that black holes can emit information. A quantum extremal surface appears and the entanglement entropy of the of the radiation, the Hawking radiation, drops off. So there are many such assumptions. But basically, what is the information paradox? That where the information of the objects that fall into a black hole goes, right? So it may be that our entire universe is just a hologram. What's a hologram? We all know what a hologram is. It's basically a two-dimensional sort of sticker, but it appears three-dimensional to us. Similarly, the hologram is actually two-dimensional. It's a sticker which is pasted on books and all. But it appears three-dimensional because it contains the information of the three-dimensional objects. Every information it has, but all the information is etched on a two-dimensional plane. That's the difference. So same thing, the surface, the boundary of the sphere is two-dimensional, but the interior has a higher dimension. But everything in the interior has an exact counterpart in the boundary. The dimension doesn't matter here, because the information content is the same. So that's why there is a correspondence between these two, AdS and CFT. So how this helps? One example is the information paradox. Then in string theory, we know that string theory demands the existence of more than 4 dimensions, space-time dimensions, which seems strange to many of us. So there is the concept of AdS CFT correspondence may explain why string theory requires higher dimension. The strings may sit in the anti-de Sitter space, which has a higher dimension, and our universe, can be just like a hologram. That's why AdS CFT correspondence is also called holographic duality. And so that's one example of why AdS CFT correspondence is useful. There are many more examples. Actually, string theory has more dimensions. This can be explained by, this cannot be explained, but maybe the concepts of Calabi-Yau manifold and many other such concepts are there. They will be helpful in explaining how the higher number of dimensions, the extra dimensions rather, how they can be compactified and maybe they are curled up to a very small length or something like that. Okay, but that's not the point. And basically in physics today, there are two major theories. One is general relativity of Einstein. So general theory of relativity explains the gravitation as a consequence of curvature of space-time. So it's basically a theory of geometry, a theory of space-time. And on the other hand, we have quantum mechanics. Like general relativity deals with astronomical phenomena, like very large phenomena, what goes on stars, galaxies, gravitation, and so on and so forth. Quantum mechanics, on the other hand, deals with atoms, even smaller entities, electrons, protons and neutrons. Then you have quarks and the elementary particles, neutrino, and so on and so forth. So these quantum mechanics and general relativity. Quantum mechanics explains 3 forces of nature and unifies 3 forces, and general relativity only describes gravitation, which is just one force. Now the unification of these two theories will be a unified field theory, which will describe all the possible interactions in that is possible in this universe in a single theoretical framework. So that is what we mean by unified field theory or final theory. And one common misconception is that a final theory, if we ever find one, that would be the end to physics. That's not the case. Final theory will not end research in physics. Final theory is just will just take us one step forward in our quest to understand the fundamental nature of reality. That's just a single small step forward, nothing else. So AdS CFT correspondence may help us a lot in understanding why these two theories are different and in unifying them. Now string theory may be one candidate theory for a theory of everything, but string theory we cannot conclusively say that string theory is a theory of everything because many other problems remain. So that is the basic idea of holographic duality of AdS CFT correspondence and why the idea is such an important one in modern physics. So I hope you find the video like useful, and that's all for this video. Thank you very much.